Yeah, so we're recording now. What I want to talk about, or this first kind of chapter that we're going to talk about, is titled Functions and Graphs. And this first chapter is going to feel very much like the first chapter from Algebra 3-4. So if you remember your Algebra 3-4 first chapter from last year, at least if you had my class, it's going to feel pretty similar. So we'll start with a definition. This definition is going to be a function. And then when I do ST like this, abbreviated, that just is an abbreviation for the phrase such that. It's fairly common in mathematics, but if you haven't seen that, that's what that little abbreviation means. So we say that a function from the set B to the set R is an assignment such that every element in B maps to exactly one element in R. This set D we refer to as the domain. That's where our beginning of our assignment happens, and the set R we refer to as the range. That's the destination of the assignment or mapping. And we talked a little bit about the definition of a function yesterday, right? We reminded that when we did a little bit of Algebra 3-4 review. Everybody feel comfortable with the definition of a function? When we represent a function, what were some of the different ways we use to represent a function? Okay. Good. What else? An equation, I heard. Yep. Okay. Yep, an XY table or T table. Sure. There's two more that I'm looking for. So sigma notation was what we used to represent series. Okay, good. So Bella says a set of ordered pairs. That's good. And then the last one was what we called a mapping diagram. And this is the one that I'm going to use to kind of draw some examples of things that are functions or not functions. So if you remember what a mapping diagram looks like, is we drew two circles to represent the sets D and R, or the domain and range. So inside of the set D, let's say we have 3 elements. We'll call them x1, x2, and x3. Inside the range, we have 3 elements. We're going to call them y1, y2, and y3. And let's say that we've paired our values this way. Is this a function as we've drawn this? Yes. So it's a function because each of those individual x's is uniquely paired to a single y, right? What if we had this pairing? Is this a function? I heard some yeses and some nos. So, okay, so the people that say no, what's the issue? Okay. Yeah, not every x is being paired. We have this guy that doesn't have a partner. So technically that one is not a function. Okay, good. Sam.
No, it has to be exactly one line.
So which x is paired with more than one y? None of them, right? So this is a function. Now consider instead if we had this one. That one is not a function. What's the issue on that one? This first x is paired with 2 y's instead of just one. Everybody feel okay about identifying whether a mapping diagram is representing a function or not? Yes. We've covered, I think, about all the different cases that you could have there. Let's talk about an equation. Next. So let's say we have the equation y squared, or y equals x squared plus 2. Is this representing a function? Olivia, you're shaking your head. Yes, it looks like. Why do you think yes? Well, you're correct. It is a function.
I don't know why.
Okay. Does someone have a good reason as to why we know that this is a function? That is true, but it's not a good reason. David, what did you say there? So this is specifically, you recognize this, it's a quadratic equation, or quadratic function, right? You know it's a function because it's quadratic. All polynomials are functions. So if you have the y by itself and a polynomial with x's on the other side, every single one of those will be a function. So, yes, that is a perfectly reasonable reason. In addition, you could say that if I drew the graph of this, it would look like this, which certainly passes a vertical line test, which was one of the techniques we could use to determine if the graph represents a function or not. So that's valid as well as terms of justifying why this would be a function or not. Can someone give me an example of an equation that would not represent a function? David. Well, you mean something like this, yes? That is still a function. That's a radical function. It's a little bit tricky to do this. Sam, you have an idea?
Oh, I was going to say if they were just both on the same side, but then you could just subtract the line.
Yeah, so like if we had this is just the equation of a line.
Right.
So this is still a function. Andrew, you have an idea? X equals 2 is not. Why is this not a function?
Wow.
It's just a vertical line, right? It's the least functiony thing you could write. Okay, if we exclude these vertical lines, can someone else give me an equation that doesn't represent a function? That was very good though, in terms of coming up with something. I heard somebody whispered something that was a good idea. Someone said circle. Yes? Okay, do you remember how to write the equation for a circle? Sam?
Is it x squared plus y squared equals r squared?
Yeah, so in this case, maybe we'll pick r to be 4. So that's a great idea. Hopefully from your geometry course, you remember at least talking about the equation for a circle. That's what they always are of the form x squared plus y squared equals r squared. So if you see specifically the issue is these y squareds, if you see a second degree y variable, probably not going to be a function. The two that we've listed are probably the most common two examples people would come up with. If we did this, if we stick the absolute value around the y variable, similar thing is going to happen. So usually to get something that's not a function, you have to monkey around with the y instead of the x. Those are all good examples, though. Okay. If we talk about a graph, I should include equation here as we changed gears. So let's say I have the graph represented here. Is this a function? No. Why not? Yeah. It fails the vertical line test. So what the vertical line test says, if there's any vertical line I can draw that intersects the curve more than once, it would not be a function. So let's say we have this. Is this a function? Yeah. What if I add in also this point here? No. It would no longer be a function because I can draw this one vertical line that intersects the graph now more than once. So a line with an extra point on it will now fail to be a function. The line itself definitely was a function. But if we include one extra point somewhere on that line, or somewhere else not on the line, it's no longer a function. Does everybody feel pretty good about that idea? Okay. So here's a set of ordered pairs. Is this representing a function? And you say no. Why? Yeah, so the issue is just the repeated x's. The y's can repeat. That's not a big deal. But the x's are a problem. If we drew this as a mapping diagram, we'd have 3 going to 2 different places. 3 would go to 2 and would be going to 8, right? So that's what we're looking for if we have a set of ordered pairs, is we're looking for repeated x coordinates. And as we mentioned, does it matter if the y coordinates repeat here? No. Not in determining whether it's a function or not. And then the xy table, is that any different than this set of ordered pairs? No, you would just be looking, again, for repeated x coordinates, right? So if you had an xy table, that looked like this, again, not a function, we have repeated x coordinates. We feel okay about negotiating these different forms that we can represent a function in and determining whether something's a function or not by looking at the form. Probably the trickiest one is the equation one. And in general, what I would say to you is if the equation looks like something we did in Algebra 3-4, it's probably a function. If it doesn't look like something from Algebra 3-4, you should be a little suspicious about it. And then probably your best check is to just try to graph it on your calculator to see if you can use a vertical line test on it, if you're in doubt. Time for a new definition. So when we talk about function notation, basically we're just saying f of x equals, and then the rest of our equation as opposed to y equals. Where this comes from is if I have a set D that contains these different x's, and I apply a transformation of f to it, each of those x's, what I have as a result is f of x1 is the transformation f applied to that x1. That's where this notation is coming from. Really, as soon as you see that, though, you can just think of it the same as a y equals. Fundamentally, it doesn't really say anything different, but I just wanted to give you an idea of kind of where that notation comes from and why we're using it the same thing as a y. Because what are these little guys over here usually called? Those are our y's, right? The result of whatever we do to the x. So they're really talking about the same thing. So for example, if we have f of x equals like 3x minus 4, we give this variable x a special name. We call it the independent variable. because we get to choose what the x is. And then the result here, the y, is the dependent variable, because to calculate that, I need to know what x is. So if I pick x to be positive 1, the result then is that the y would be negative 1. Everybody can see that? If I pick 1 for x and plug that into the equation, the result is negative 1. So the y value depends on the x value. But I can pick any x I want to plug into that equation, right? I'm not limited in any way. And in no way does the x depend on the y, right? Do we feel okay about the function notation, kind of what that's representing? Again, this is an Algebra 1 idea, so hopefully that feels pretty comfortable. Next up is domain and ranges. And to describe these domain and ranges, we're going to use something called interval notation. And an interval notation is just a way to describe an infinite set. So assume, say we have the set of x's from, say, 3 less than x less than or equal to 5. If I was going to translate that into interval notation, I'm going to be talking about the numbers between 3 and 5, right? So I'm going to have 3 and 5. The numbers, when I write them for my interval notation, should always be going smallest to biggest as we go from left to right. If you wrote 5, 3, that doesn't make any sense because there's no numbers that are between 5 and 3, right? Should be in ascending order. And then we need to indicate with a symbol on either end that 3 is not included in the set, but 5 is included. And the way we do that is we use the symbols of a parenthesis for not included and a square bracket for included. And I guess in this case, since we have the x's between 3 and 5, we should say x is a member of the interval from 3 to 5. So that little symbol, that little E-looking symbol there, just is mathematical shorthand for the phrase like member of or element of the set. So again, mathematicians, we love our little symbols and shorthands. I'll try to do my best that as I'm using symbols and shorthands to let you know what they're representing. I think so far I've done a pretty okay job of doing that, right? If I use some symbol you're not familiar with, though, please, or some shorthand that you're not familiar with, please interrupt and ask. Let's do another one of these. How about x is greater than 2? Yes, Sophie. Yes, so the smallest number that we're concerned with here is 2, and the biggest number is infinity. I like to put a positive or negative in front of my infinity just so I don't confuse myself. You don't need to put the plus sign in front of your infinity. I just do that because that's what I'm used to doing. But it's correct to not include the positive sign there if you don't want to. Should the 2 be included? Should I use a bracket or parenthesis here? Parenthesis. And is infinity an actual value that x can equal? No. So should it get a bracket or parenthesis? Parenthesis, because that's never included in our set. We can't have a set with an infinity in it. Good. Let's do one. Oh, and then again, probably do x as a member of, since we talked about x's here. So here we have y is less than 2, or y is greater than or equal to 5. So probably the first thing we need to talk about is how are we going to deal with this or situation? Does anybody remember what we do with this? Sophie. And what goes in between the 2 separate ones? The U. Very good. So this is the symbol for, that's the symbol for union. So that's the connector that we use in an OR situation. That's what that symbol means. So notice it's like a capital letter U with no tail on it. So the first interval we are interested in is y is less than -2. So what is the smallest thing that we're concerned about in negative infinity? And the biggest thing is -2. And on the infinity, parenthesis or bracket. See? On the -2. On the y is greater than or equal to 5 part, what 2 numbers are we concerned with? 5 and positive infinity. So 5 is the smaller one. Positive infinity is the bigger one. So we'll go 5 first and positive infinity second. On the 5, parenthesis or bracket. Okay. On the infinity, parenthesis or bracket. Parenthesis. We remember doing this? Feel okay doing this? Good. You probably did a lot of this last year. Oh, and again, since we're talking about y's, we should probably say y is a member of. There. Being a little bit more precise with our notation than we were in Algebra 3-4. I was pretty lax about doing that notation there. Try to tighten that up a little bit as we go deeper into our mathematics career. We get a little bit more strict about using our notation correctly. So we're going to write our domains and ranges using these interval notations. So let's talk about writing the domain for some examples. So on a question like this, we really have to unpack a couple of things. So there's really 2 things that we could be talking about here. We could be talking about an implied domain versus a relevant domain. So an implied domain is based on the context of the course. What is like the largest set that we could be talking about? In most of your classes, that largest set would be the real numbers. Almost always the implied domain we're talking about is the real numbers. Now, in this case of this f of x, can I plug any real number into this and get a real numbered answer result? No. What is the issue? The square root. Why is the square root causing an issue? Give you a what? Not a decimal. That's not the issue. Decimals are fine. That's the issue, that if I square root a negative number, I get an imaginary result. That's a non-real result. That is my issue. Everybody okay with that? So to find my relevant domain, I need to make sure the part underneath the radical is greater than or equal to 0. Right? As long as it's not negative, I can evaluate this function. This function evaluates and has a real numbered result. So if I add 4 to both sides then, I get this. Which I can write in interval notation. Everybody okay with that? So again, the implied domain here would be all real numbers. There's nothing algebraically that tells us any differently. That's, in the context of this course, that's almost always what we're talking about, is the implied domain. The relevant domain, though, can I plug any real number in this and get a defined result? Andrew's shaking his head no. What's the issue, Andrew? Yeah, so the issue here is if I have a 0 denominator, this expression is undefined. So I know that x plus 2 cannot be 0. If I subtract negative 2 from each side, I know that, or if I subtract 2 from both sides, I have x cannot equal 0. How do I write that using interval notation, though? So basically what I have is x can be less than negative 2, or x can be greater than negative 2. Everybody agree that that's the same thing as x cannot be negative 2? And if I do that, then this looks very similar to the example above, right? Where I have negative infinity to negative 2, union negative 2 to positive infinity. Yes?
Just to be
Correct.
Okay, so you have it.
Oh, no, these are the relevant domains. The implied domains for each of them were all real numbers. The relevant domain is what we've settled on. That is the domain we're often actually interested in.
Okay, wait, how do you know it's all real numbers?
So from the context of this course, the set of numbers that we kind of work with fundamentally is going to be the real numbers.
Oh, okay.
Right? So it's almost the implied domain is almost always going to be all real numbers.
Okay.
If we're in a more like a different, like advanced math class, maybe the implied domain would be the integers,
Okay.
or it could be the complex numbers, or it could be the rational or the natural numbers. But in this course, really we're talking about real numbers as our fundamental set that we're working from. If you went back to elementary school, really your implied domain is like the natural numbers. You're just worried about positive whole numbers, right? That's the only thing you're considering in those courses. That would be kind of the implied domain if you're doing anything like that this in elementary school, but you probably wouldn't be. Yes. Or in a very oddly structured elementary school class where we're talking about functions inside of an elementary school classroom, which you probably could do. Kids could get it. You'd have to approach it differently. So our last example here we're going to look at is V of S equals S cubed, where V of S is the volume of a cube with an edge length of S. Hopefully you recognize that formula from your geometry class when talking about the volumes of a cube. If you don't, that's okay, but you should recognize me. It looks familiar. So again, our implied domain, because the context of this course is all real numbers. The relevant domain is I would probably accept that, although I would say there's a slightly better answer than positive. Well, positives don't include 0. I would say you could probably include 0 in this. So I would say non-negatives is the way you include the positives, and 0 is the way you say that out loud. So I would say that this is kind of our relevant domain, because we know the side lengths of a cube could never be negative, right? I assume that a 0 side length cube is just a cube that doesn't exist. It would be like a singleton point. Whether you want to count that or not, I wouldn't be so picky about on a quiz or a test setting, whether you interpreted that as greater than or equal to 0, greater than 0 in this setting. I don't know that it's entirely clear without a very formal definition of what we're counting as a cube, whether you should include 0 or not there. So I would be pretty flexible about that, or very specific, have a very specific definition of what I mean by a cube. So turning this into interval notation, in this case, we have 0 to positive infinity, including 0. All right. Everybody feel okay about finding these domains? Okay. Good. Let's talk about ranges then. Finding the range for something is almost always going to be considerably more difficult. One way we can always use to find ranges is we can use our graphing calculator. Although I'd like to spend some time here now talking about how to do it without using our graphing calculator, using a little bit of intuition. So we're going to go back and look at these 3 examples that we just did. I'm going to do work alongside of them. I'd encourage you to do the same thing. We're just going to be finding ranges now. But I'm going to need to use my domain in order to find these ranges. The reason is because the x, or the domain, is the independent variable, but the range, or y, is dependent on those x's. So I really need to know the domain in order to find the range if I'm not going to just graph this on my calculator and look at the picture. Everybody okay with that reasoning? Okay. So we'll go back to the first one. So I'll do the range stuff here in blue, just to be, so it's a little bit clearer when we're looking at this. All right, so the first thing I want to do is I want to look at the function itself and decide if this function is like increasing or decreasing everywhere. All of these finding of range things become much easier if the function is increasing or decreasing everywhere. So the way I'm going to think about this in my head is I'm just going to think about like y equals the square root of x. Okay? As x gets bigger, what happens to the square root of x? It also increases, right? So like the square root of 1 is 1. The square root of 2 is 1.4-ish. The square root of 3 is 1.7-ish. The square root of 4 is 2. As x increases, the square root of x increases, right? So I know that this is increasing. So I know my range then. If my domain is going to positive infinity, my range must also be going to positive infinity. Because as the graph moves to the right along the x-axis, it has to be increasing up the y-axis as well. Does everybody follow that reasoning? Okay. What I need to find, though, since there is a minimum x value, there has to also be a minimum y value. How would I find that minimum y value? Yes, Joanna? That's exactly what I would do. So I'm just going to plug that minimum x into f of x and evaluate. What do I get when I do that? 0. I heard somebody whisper. Say them loud if you know it, so you can look smart in front of everybody. You won't look dumb if you know the wrong answers, but if you don't say anything, you're never going to look smart either. And because 4 is included, what's going to happen to 0? Also included. Is everybody clear on how we got the 0 there? Okay. Does that feel reasonably comfortable? All right. Let's look at B. Is this one going to be easy to tell where it's increasing and decreasing at? Not as much, right? Why not? It's because the positive and negative is going to be going on in the numerator and denominator at different times. Makes this kind of difficult to tell when it's going to be increasing and decreasing, right? So maybe we take a different tact at this. Let's think about it this way. Let's maybe assume, because if I look at the domain is almost all real numbers, right? It's just everything except for this specific x value. Everybody agree with that? So I'm going to assume the range is everything except for, is also potentially very close to all real numbers. Let me put it that way. Everybody okay with that reasoning? And we can see that if I just picked like some arbitrary values, like if I say, what if y is 4? Can I solve for 4? Is that a bad example? Just want to make sure. No, I don't think so. It's not a bad example. I had to check for a second. Could I solve for x here to find out that pairs with a y of 4? And almost everything is going to be okay to do that for, right? Okay. Where the issue is going to come in, or where would the issue come in at? Can anybody see an issue that we might have here? Okay. That's fair. It's fair. If nobody can see what the issue is, that's okay. Again, like, you didn't... Okay, so let's start over here. That's okay. So let's maybe look at it this way. So we have 3x over x plus 2 equals y. What if we find the inverse for this? So to find the inverse, what we want to do is isolate the x variable, right? So to do that, let's cross multiply. And then we can distribute that y through. We can move all the x's onto one side. We can factor off an x on that left-hand side. And then divide both sides by 3 minus y. There absolutely was a way to look at a rational function and tell what the... Oh, not the inverse, but you could tell what the range was going to be by just looking at it. But this is... There's a bigger point for me doing it this way. But no, it's difficult to tell just by looking at a rational function what the inverse is going to be. So this is what the inverse kind of looks like, right? We still would have to swap the x and y, but we're going to stop here because this is all that we really need to go forward. What values of y are going to get us in trouble here? Oh, sure. Thank you. So Gabe says, I forgot my y here. Very good point. Thank you. I did forget that Y, so note the purple Y there that I added in. Maybe I should have picked a color other than purple. That might be hard to see. No, I used, these are in purple. The other stuff was in blue. Yeah, I mean, you're far away, it's hard to see. Okay. So let's reel this back in. We looked at this and we tried to determine what the range was going to be, but we couldn't reason it out just by looking at it. Right? So what we did instead was we found the inverse. The process that we used to find the inverse, but we didn't bother to swap the x's and y's. And in fact, you wouldn't want to, because what we care about is which variable? Y. If I look at this, is there a value of y that's going to get us into trouble? Yes. Here I can see immediately that y cannot be 3. So there is my range. 0 for y is okay, because you just end up with x equals 0, which is fine, right? If I have y equals 3, I have 6 over 0, which is undefined, and that's a problem. So we would say then y is an element of So if you're not sure how to find the range, you can find the inverse and use the inverse to kind of determine the values for y that would be acceptable, the same way you did for the domain. Isabel?
So if you have like a, I don't know, scenario where you expect to see like the work. Right.
Yeah.
I gotta just plug it into a calculator.
You can certainly use your calculator to kind of know what the answer is, but I would want to see work to justify what you got,
Alright.
for at least for full credit on something like this.
Right.
And that's a fair question, certainly, to ask about what the expectations are. Those are important questions to ask. Andrew. I don't want to say the only way to do it, but if you're not sure what to do, that's often an easier way to recast it as, now it's just like finding the domain, right? If I find the inverse, now I can treat the y just like I would for finding a domain, and it's usually pretty easy once you've done that. But there is a shortcut, because I know this is a rational function. There is, immediately I could look at this and say that I knew that what the range was going to be. And last year, you would have remembered exactly how to do that. The shortcut for this one was, because this is a rational function, and in fact it's a simple rational function, but since the degree of the numerator is the same as the degree of the denominator, I can find the horizontal asymptote by looking at the leading coefficient over the leading coefficient. So 3 over 1 is where the horizontal asymptote is. So the range is everything except for that horizontal asymptote. You knew that last year, you just forgot in the interim, which is okay. That was a very... Yes. Yes, I would have still shown you this method too. Because it's not... Excuse me, guys. I would have still shown you what I did there, because we're not talking about rational functions right now, and I would not have expected you to remember that trick. The point is kind of developing something that's general enough that you can use regardless of what the function looks like. So looking at whether it's increasing and decreasing, and just if it's one-sided, like we did in the first one, is helpful. Or in this case, where it's like, can't really tell the increasing, decreasing part of it, which is fair. What can I do then without knowing some really specific rule about that kind of function? Okay? Okay. Let's stop here, right? We have 3 more minutes. So, for tomorrow, do we meet tomorrow? Okay. For next time,